Hello, Physics 135 students, and welcome back for week 4. This is our fifth lecture, and we'll go ahead and start by leveraging the icebreakers that you've been responding to so far. I'd like to try to build a little bit more community in the class. It's tough, of course, it being an online class. I'd like you to reply to someone else's introduction from class number 1, and then I would also like you to reply to one of the icebreakers that someone posted recently, and then, of course, to post your reply to the icebreaker on the next slide. So today, the icebreaker is if you could be any two of the following, which would you choose? So you could be a football player, or a king, or in space. And for my own answer, I think that I would choose to be a king in space. That sounds pretty fun. I do like playing soccer, which I guess is, the European sense of football. I lived in Germany for about 2 years doing my postdoc, and they would call American football egg ball. At least some people would, not everyone. Um, and then fun fact, there's also a Australian sport which they call football, which is kind of kind of more similar to rugby is what I think, but it's kind of like American football but different, kind of like soccer but different. So maybe there's some other sense, but those are the only three that I'm aware of. Anyway, go ahead and please pause the video. Make sure that you handle the community building aspect, reply to someone else's introduction, and ideally also reply to someone's icebreaker, and then 3, post your own response to this icebreaker. Okay, so hopefully you paused the video and handled everything. Now, moving on for today, we is a little bit lighter in terms of the lecture because we're going to have double the number of activities compared to usual. There's just quite a few things that I think would be really helpful for you to, you know, experience for yourself. There's only so much that we can do via a lecture for some of these activities, in my opinion. Um, so the idea for today will be to have something like a 30 to 45 minute lecture. I think a little bit closer to 30 minutes, but we'll see. And in other words, the majority of the quote unquote lecture time, the idea is that you will be working on different worksheets and activities that'll be posted on Brightspace. So to start with, I kind of want to follow up with what we were talking about last class with the scientific revolution that Galileo really did a tremendous job of cementing. And key to this was not Galileo inventing a telescope. Again, that's kind of debated, but Hans Lippershey at least holds the patent that's, I think, fairly recognized. But Galileo was the first person to point the telescope to the sky. So let's better understand how these telescopes work. And to start, we have to better understand how our eye works. So there's quite a bit of biology. I have not taken any sort of formal biology schooling in about 18 years. But the most important parts is that the eye is composed of a lens itself. The way that we see is on the retina, there are rods and cones. The rods and cones are allow us to see just in grayscale as well as with color in terms of the cones. And so what this lens does is, otherwise we wouldn't have any light that's able to get way up here, way down here, typically, right? So the lens allows the light to refract and bounce and hit different positions. And then also, like our pupil is helpful for allowing some of the light to get, so that's not just like this little narrow window, but we can see stuff that's above us as well as below us. All right. And so, in terms of understanding that refraction process, that is really core to how we see and core to how telescopes work, the idea is that the speed that waves propagate depends on the medium. So you can imagine this if there's like a marching band. I know it's not Purdue University, but I was really excited to see Indiana University win the college football championship. I thought that that was pretty cool to see. Anyway, so if you've ever seen a marching band, and usually there's a bunch of people that are all lined up, but if they're marching at the same kind of rate, if you will, um, it'll be easier for them to maintain a certain speed on the sand compared to in water. They're going to start lagging in water, would be the idea. And then maybe a little bit closer to home, if you've ever been off-wheeling or uh, maybe intentionally, maybe unintentionally, when your wheel first gets into like the mud or off the track, the wheel that is off track will not rotate as rapidly as the wheel that is on the track, right? So you will typically bend or turn in the direction of the slower medium. So, for example, in air, light travels at a constant speed in vacuum, but light travels at a different speed in different materials. And air is very close to vacuum, but it's light travels a little bit slower through air and then substantially slower through glass, though. So we can really notice this effect. And if you take Physics 251 or perhaps the non calculus based second semester intro physics class, then you really get this fundamentally through the labs. Um, again, the idea is that if you imagine a car driving along a road, whichever wheel hits first is going to travel more slowly. So in this case, the left wheel, if we imagine this going down, the left wheel will hit the glass or hit the mud, we could say first. It's going to go slower. So that's what causes this to bend, more towards the horizontal. All right. And in terms of another example of refraction at play, aside from our, just directly in our eyes, there's also refraction that happens due to Earth's atmosphere. And the result of this is that when the sun is setting, it's not like we see a perfect hemisphere like the moon. Instead, for the sun, there's this weird kind of like egg shape pattern that appears. And you can see that the sun is significantly more orange or red on the lower side because there's more of Earth's atmosphere that we are seeing through compared to at higher angles. All right, and then these I'd really recommend that you take a look at yourself. We'll take a look at one or two of them together. So at CU Boulder, they have these really fantastic animations on how refraction works. So, and they have a lot of control here. So you can turn on the laser, you can adjust which way the laser is pointing. And we're not going to really talk about total internal reflection, which, so in addition to a refracted ray, there is also a reflected ray, unless you bend the angle like sufficiently. And in this case, I am not quite able to do it, but if I switch my materials, for example, then we only have reflection. So this is called total internal reflection. Anyway, if we go back to air and say water, you notice that there is a certain angle. If I switch this to glass, then again, you can imagine like a Jeep or some sort of truck hitting the mud. And the stickier that mud is, the slower the wheel is going to turn, the more the angle changes compared to if it's almost the same as the road, then you're not going to notice much, of course. Okay, so this is, again, one of these FET demos, and you can play around with it, and I think the waves are pretty mesmerizing. You can adjust the speed and pause the video, etc. And now, if we go ideally backwards, then there are some other demos here. And maybe you all can explore the more tools one. The Prism one, I think, is quite nice. So let's go ahead and set up a prism. And so you can see that the light bends not just once, in fact, but it bends twice through this prism. And again, in a intro physics, in another physics class, you learn more of the details of Snell's law of refraction. For our purposes, it's a bit more qualitative that refraction plays a fundamental role in how light moves through uh, glass elements or optical elements. Okay, going back to the slides. So we've seen how refraction works. Now, in terms of the utility for telescopes, the idea is that you have a lens that is used to capture the light at a particular point, which is what we call the focus. And our eyes work the same way, where we have initially parallel rays. As they pass through the lens, they end up with a focus, ideally on the retina. If you're nearsighted or farsighted, then you have the focus point either before the retina or after the retina. And therefore, you can use glasses, which are, of course, another lens to fix that and make sure that the focus is actually on the retina. Now, in terms of the image formation, one thing to keep in mind is that a lens will actually invert images. And then our brains are able to handle this perfectly fine. In fact, for funhouse mirrors, if you flip kind of your vision again, it's initially pretty trippy, but the brain figures it out pretty quickly. And then, of course, in space, this by and large doesn't matter, and we don't really notice it. But for birding telescopes, for example, they will always use two lenses so that you don't notice the inversion. And for capturing images in the modern era, going beyond Galileo, the idea is that we use cameras, typically charge coupled devices, although most phones use CMOS detectors. In both cases, they work in a kind of similar-ish way, where you're receiving photons that excite some electrons that then get read out in the electronics. Now, going back to uh, the telescopes, Galileo had a much smaller telescope than this, but ultimately it was a refracting telescope. The problem with building like larger and larger refracting telescopes is you need a corresponding larger telescope, which means, for one thing, you need a larger dome. And then the challenge is that you have to kind of pincer the lens at the very end of it. It's not supported at all. And glass will, although we think of glass as being, a solid, it'll end up distorting and sagging under its own weight. And this causes deviations and ultimately a lot of problems. So the world's largest telescopes these days are reflecting telescopes. And if you want to learn more about the world's largest telescopes, definitely take another astro intro class. We might talk about them a little bit more later on in this course. And definitely in terms of the world's largest telescopes, the book goes into quite some detail about it. I think it's pretty fun historically to hear about the development of the larger and larger telescopes. Now, back to Galileo, he did not have a huge telescope. In fact, it was only a little bit larger than the human eye. The average, people have different size eyes, of course, but the average human eye in diameter is about 1 inch. Galileo's lens was about 1.5 or maybe 2 inches. All right. So that's kind of the summary on this topic. So now I'd like you all to do a little lecture pause and uh, yeah, I didn't manage to construct anything exactly related to refraction, but and still in follow-up to our last lecture where you all learned about Newton's laws, I'd like you to pause the video and work on the Newton's laws worksheet. Okay, so unpause. Hopefully you did the Newton's laws worksheet. And next we're going to do, really there will be 3 different worksheets as well as more attention checks throughout the rest of this lecture. And we'll be getting into the core of what is science as well as the method that we can use for science, which is really, really helpful, especially if you're interested in doing a quantitative research project to understand the key steps that are involved in any really successful project. Even if you're not really thinking about it, it can be helpful for structuring your project. All right, so if you've taken a course with me before, you probably have seen this, but nevertheless, some of you have not taken a course with me for sure. So hopefully you find this quite fun. So first, go ahead and pause the video and think about who fired the first shot. We have Joe, John, and Jim. Joe is on the left. Sorry, I guess don't pause the video quite yet. Joe is on the left. John is in the middle. Jim is on the right. You can see that each of them have some circles. Joe has a blue circle. There's a blue circle for where his bullet, or maybe it would be better described as a paintball, ended up landing. John is in the middle. John's paintball bullet or whatever is in the middle, and then Jim is on the right. So go ahead and pause the video and try to think about who fired the first shot for a minute or so. Okay, so unpause. Hopefully you actually paused the video and thought about this a little bit. And now I want you to go to Discord as well as email me, of course. And on the Discord, I guess I'll mention that this time I created some threads. So you should be responding to this first thread in the lecture discussions channel. Okay, so make sure that you go and pause the video and share what you were thinking for attention check one. Okay, so unpause. And then next thing is, all right, you were asked to like think about this, about who fired the first shot. And maybe you already had some, well-developed theories in your mind about what was going on. But really for science, the idea, of course, we want to explain things, but the first step is really to make observations. So for attention check two, please jot down at least two or three observations you can make when looking at this picture. And these can be any sort of observation, doesn't have to be necessarily relevant towards answering this question, just any sort of observation. Pause the video. Okay, unpause. Hopefully you jotted down two or three observations. Next, the idea is to get a little bit more specific, and of the observations you listed, or maybe some additional observations you can make, which do you think are relevant and important for addressing this question? So go ahead and pause the video and try to address attention check three. Okay, and then moving on. So for science in general, again, the goal is to explain something. And there are many different observations that one can make that are still not, of course, explanations. So one could observe that Joe and Jim are angled towards each other. In other words, perpendicular to like this, maybe not whiteboard, but this piece of glass or mirror or so. Whereas John is facing away. So maybe John fired his shot and then had more time to look away. That'd be observation plus some rationale or explanation. Another observation is that Joe has two buttons, John has two buttons, and Jim has two buttons. It's probably not a relevant observation, but it's still an observation one could make. Another observation is that Joe and Jim have kind of gray or beige-ish colored suit jackets, whereas John has a bluish colored suit jacket. And this is supposed to be difficulty one, so maybe, although that would otherwise one would expect to be not relevant, maybe it is. John and Jim both have reddish neckties that are visible. Joe does not. Presumably not relevant, but still an observation one could make. Probably one of the most relevant observations one could make is that John has, from his paintball bullet or whatever, there are lines that go all the way to the edges of this mirror or piece of glass. Whereas for both Joe as well as Jim, their cracks seem to stop where John's run through. suggesting that John's bullet hit first, and then Joe's ended up getting blocked in terms of crack propagation by the cracks that John had already made, and similarly for Joe. So in terms of making explanations, notice that I wasn't really. Another explanation could be John fired first because cracks. And that would not be a good explanation because it doesn't let someone really understand your thought process. If someone cannot understand your thought process, then it's not really an observation. If you also take what someone else is mentioning, like from a paper, if you're writing a literature review, and you end up just really repeating the exact same phrases, then one, that'd be plagiarism. But if you still like paraphrase a bit better where it's not plagiarism, but really just um, use the exact same phrases, even if not the exact same sentences, then you're kind of being like a walking, talking thesaurus, and that's still not really explaining in your own words. So to try to help you better understand what is science, we had that first kind of lecture activity. Now we have the first of our lecture or worksheet activities. I'd like you to work on the Tangram worksheet that is posted on Brightspace. This one, you will need to print this out. You could, I guess, technically be creative and just take a blank piece of paper and trace something. But I would really recommend printing out the Tangram worksheet using scissors to cut out the shapes and then see what are the simplest shapes that you can make, both for the first part as well as after some new discovery is made. So I don't think this will take too long, but it can take you some little bit of effort to go to a library if you need to, or to do the printing and the cutting out. So please pause the video and work on the Tangram worksheet next. Okay, video on pause. So next, I want you to think, and this is the next attention check, on really what constitutes science, just in your own words or in your own phrasing. And there's no right or wrong answer for your initial thoughts here. So pause the video and handle attention check 5. Okay, unpause. So for the purpose of this class, I mean, if we were in person, it'd be really nice to be able to discuss this and maybe try to come to some sort of class-wide consensus. But for our purposes, I'll make the claim that science is ultimately something intuitive. There is some sort of problem, and then science is ultimately a manner of addressing that problem and coming up with a solution or a fix. So let's go through a couple of examples here. Let's say that my car isn't starting, which definitely, in terms of winter weather, is rather more of a concern for my junker at this point. Uh, I'm not a huge car person, although I would like to get a somewhat nicer car someday. Anyway, for now it's the A to B, and it certainly works. It's a 1998 Chevy Suburban. I still love it, honestly. Um, okay, so let's say that my car doesn't work one morning. Then I have some options, right? I can like just go ahead and kick the tires and then go back and try to um, jostle the key in the ignition, right? And then who knows? Maybe it works, but probably the car is still not going to start in that case. Let's say that I still do something maybe rather non-scientific and jam the wheel left and right. That actually worked for me one time. Uh, and that was, I guess, because there was some sort of locking mechanism with the wheel. Maybe it's an anti-theft measure, but it really was effective in me not starting my car one night, actually, rather than one day. Um, and so sometimes you have a kind of nonsensical solution, and sometimes it works out, or sometimes, as in this SpongeBob episode, it ultimately doesn't work out that well. So ideally, we want something a little bit more tried and true, something that will be a mechanism where even where there's a situation that we've never encountered before, we can follow a set of steps and still come at a solution. So keep in mind that science is not really the solution itself, it is the arrow. It's about how we go from the problem to the solution. And keep in mind that science has limitations. We've talked about in some of our previous sessions about the development of natural philosophy. And science is ultimately really the evolution of that natural philosophy. And so, in particular, science doesn't address really weighty questions like ethics or other branches of philosophy, which are certainly important, but it's just not within the purview of, again, natural philosophy or of science, of being related to physical causes and effects. So, regarding the scientific method, you may have learned, a variety of. If we were to go around the classroom, it could be that each one of you has learned a slightly different scientific method. Probably that's not the case. Most students come in with a 7-step scientific method or a 6-step scientific method. For the purpose of this course, will be even a little bit simpler than what most of you have probably encountered previously, unless you've taken a class with me, of course. We'll consider a 5-step scientific method, which we'll abbreviate with oh heck to try to keep that easier to remember. Or I guess you could rearrange this um, to keho, but I would not recommend that. I'd recommend going in the order of oh heck. So first for that O is observation, just like we did for the who shot first activity. The idea is to start really by collecting the information that you have accessible to you. And almost naturally, we tend to jump the gun and already start to think about different hypotheses or educated guesses. But um, in terms of observations uh, within the purview of this class, when you all have to come up with your semester-long research projects. Most of you have submitted your topic, type, and target already, which is great. But for those of you that are, you have a broad topic, but you haven't really narrowed yet, one option would be thinking about the supermassive black holes that have been discovered by James Webb Space Telescope in the last few years. So this is a graph showing the redshift on the x-axis and the stellar mass on the y-axis. So anything that would be right at the bottom of this graph would be a black hole that has 1,000,000 times the material that our sun has. And up here, where a lot of these dots are clustered, is around 1 billion times the mass of our sun. And the issue is that there are some objects that are found very close to the beginning of the universe. So you can see that the x-axis redshift we'll talk more about later. The top x-axis is really the same information framed differently. It's the cosmic age since the origin of the universe. And we can see that even less than 1 billion years before the start of the universe, there are some objects that appear to have formed a lot quicker than we think would be hypothetically possible. So, depending on the initial mass of the black hole, we think that there could be stuff that forms um, pretty reasonably left, or in other words, with more time. But if the initial black holes have a mass of, let's say, of 100 solar masses, or excuse me, of only 10 solar masses, then we can't explain, in other words, if they start out like stars, and we can't really explain a bunch of these dots. We can more or less understand them if they started out a bit heavier, but we have to understand why they started out so heavy. And this one, in fact, is borderline. This was back in 2020. The situation has gotten worse with James Webb. There are now more and more of these really massive black holes that are discovered up to redshifts of, generally 7 to 10 with James Webb Space Telescope. Another example that is less relevant for this class, but much more related to my background and interests is in terms of galaxy formation evolution. And James Webb has also been key in cluing in, well, observationally, that there is a lot of material that is outflowing from galaxies. So observations, again, it's kind of hard often for us to separate the act of pure observing from any sort of explanation. Usually, the first part of an explanation is going from an observation to some sort of hypothesis. And for the purpose of this class, a hypothesis is not an educated guess. In this class, a hypothesis is a testable prediction. And ultimately, for what that testable prediction is, yeah, you could maybe frame that as being an educated guess, but in many cases, it's going to be an uneducated guess because you all are taking this as an intro class, right? And that's totally fine. So some sort of testable prediction, though, whether you have a lot of information or very little, you can still come up with some sort of testable prediction, ideally. And the testable part is key. Let's look at some different examples. For those supermassive black holes, there are different hypotheses about where they came from. Maybe they started out, again, kind of like stars, the first generation of stars. Maybe they started out with heavier masses than stars these days, where you could have seeds that are around 100 solar masses when all is said and done. But there's another option, which is that the early universe, we think, didn't have very many molecules in it because it was too hot. In that case, you could potentially just form so-called direct collapse black holes, where they just start out with around 1 million solar masses, and then it's a lot more feasible for them to grow up, 1,000 times compared to still like 100 million solar masses. Another option is that, and don't worry about understanding all this in detail, it's just an example of a hypothesis. Another hypothesis is that, okay, maybe these black holes exist because we had like stars that formed, and those stars started out in really high density environments that led for seed black holes of 1,000 to 10,000 solar masses. Still a lot easier for them to grow up to 1 billion solar masses in this case, although not as easy as in this case. And then if we can probe earlier episodes of black holes with James Webb or other telescopes to actually find the seeds or the kind of the predecessors to these billion solar mass black holes, then we can really have a test. And so in other words, we have a testable prediction for the different mechanisms that might explain the observations of billion solar mass black holes within the first billion years of the universe. So again, critical to the hypothesis as far as that testable prediction is queuing up step 3 of the scientific method of coming up with an experiment now. And let me just kind of zoom out here and mention that this is going to kind of obviously be a important topic for your quiz as well as for your first exam, if not multiple exams. So please make sure that you're trying to understand, again, not like these figures in detail, but the scientific method as presented in this class. So again, for step E, we have some sort of experiment. So in terms of, again, like my own research, we can think it's a little bit harder for me to come up with an experiment that's already been done for the black holes. That's something that's an active area of research. In my own research studying the outflowing gas in galaxies, I've run computer simulations. And so here's one example where we have a hot supernova shockwave that is really bathing these initially cold, potentially star-forming clouds. And the kind of hypothesis is that if a cloud is too small, then it'll get evaporated into the supernova like heated material. If a cloud is sufficiently large, then it will persist and potentially still form stars. And what we found is a little bit is actually like a third if then, which was not part of the initial hypothesis, actually, but there is a third possible scenario where in this case we don't think it will be star forming, but there's still a lot of cool gas that might rain back down on the galaxy ultimately and end up contributing to star formation at a much later epoch. Okay, so we have an experiment, in this case, a computational experiment. You can try to come up with tabletop experiments, although that tends to be quite challenging in astronomy. A lot of astronomy experiments are either observations or simulations, something computational. All right, and then step 4 of the scientific method, we've gone off the screen with RK, but step 4 of the scientific method is conclusion. And so this has to do with relating the results of our experiment to whether our hypothesis was proven correct or incorrect. And ultimately, it doesn't matter whether the hypothesis is correct or not. Often, the most interesting developments in science are when a hypothesis is proven incorrect, but nevertheless, we do have to understand why. So, and I mean, in some cases, we don't understand why, but we really, really want to. It's kind of part of human nature, I guess, to feel dissatisfied unless we really have an explanation sorted out. If we don't have a full explanation, usually we have to continue this process. So, in terms of conclusions, there are different ways of going into this. I wrote this as NASA black hole animation, but really it's two different visualizations. I'd recommend at this point that you pause the video and take a look at these two animations. And as far as the conclusions that one can draw, uh, really this is in some ways synthesizing information of black holes, allowing people to consider what they appear like. And similarly for this cold clouds and hot winds visualization, it's a conclusion in terms of how this looks, not in a textual sense, but in a graphical sense in this case. Another way to frame the conclusion in a bit of a more rigorous or quantitative measure would be, again, related to these cold clouds and supernova heated hot winds. We can see that if a cloud is sufficiently small, although framed not in terms of a radius, but a ratio of the cooling time to the so-called cloud crushing time. But anyway, if a cloud is too small, then it ends up losing all of its mass. We could say it dies, to be a little bit anthropomorphic. And if a cloud is sufficiently large, then it ends up surviving. So this is one way to represent a conclusion, still graphically, but a little bit more rigorously or quantitatively. All right, and then the last part, which we really often have to do if our hypothesis is proven incomplete, is to keep going. And sometimes that's within the project itself, but oftentimes, you might not have a full solution, just like dark matter and dark energy are major unsolved puzzles. Sometimes you just have to record the results of your experiments and conclude and then ask for additional people to keep going or to follow up yourself next year or in future years. All right. So in terms of one example, again, this is a little bit less relevant to our class, but so I had studied, again, cold clouds and supernova shock heated material. My postdoctoral supervisor worked with a PhD student who considered the same sort of thing, but including magnetic fields. And what they found was that, and not only magnetic fields, but a bit of a different setup, they found that magnetic fields can play a huge role in suppressing the mixing between the cold and hot phases, depending on the initial magnetic field topology. All right. And so that summarizes the scientific method, and that is the end point of our class. You can expect the next video to ideally be quite a bit sooner. This was a little bit of a challenge in terms of really trying to make sure that I kind of hit all the bases and had sufficient material for you all to cover this week. But I'm hopeful that the combination of this lecture and the 4 different activities, I don't know that I actually referenced the fourth one, but there is, so let me go ahead and add that quickly here. So there is, we've addressed three of the lecture activities so far. The fourth one, um, actually, I need to double check that we're not missing two of them now. Yeah, in fact, we are missing two of them. Okay. There we go. Okay. So, okay, here, perfect. I just didn't advance to our last slide. Okay, so for the last part of class, and again, this is more the active working part of this class, there are two worksheets I'd like you to work on. I'd like you to start with the Game of Science worksheet, which will take some time for you to go through. I expect maybe some of you will blaze through it, but if you're really trying to understand this, I think it will take a decent little bit, like 30 to 45 minutes, maybe even a bit longer. And then the last part of class will be a hypotheses and experiments worksheet to get you some more practice in terms of thinking about the how to frame whether something is a hypothesis or not. All right, so that's the end of class today. Hope that you all enjoy the different activities. If you don't enjoy them, then please let me know. Your feedback will be helpful for shaping this and improving for future iterations. I'll ideally have both more tailored activities as well as more lecture materials in future iterations. So anyway, take care and bye-bye.